And I believe that there's also recording that's done by the Canvas tool. Okay, good. So again, I just want to check before I start, everyone can hear me? Just send a message or say something. Okay, I think I heard David. Okay, great. Great. All right. So let's see, I'm going to share my screen. Go. Okay, now everyone should be able to see my screen. Everyone can see my screen now? Okay, great, great. I'll turn my webcam off because there's probably no use there. Okay, thanks, Junyi, DeMarco. I see your messages. Okay. All right, so we're going to start. We're just going to continue off of last module. Let me start up PowerPoint here. All right, and again, can everyone see the PowerPoint slide? You can see it. Great, great. Okay, so last time in class, what we covered, we started off with just got to start on Module 4, and basically these are the 4 topics that are super important that I want you to understand at the end of this module. It combines Module 3 and Module 4. Basically the 4 carrier processes. A carrier is born when it can be generated due to heat or light. So that's carrier generation. So either an electron or a hole is generated. And then once the carrier is generated, depending on whether an electric field is present, it may drift. It may move due to drift currents. It can also move due to concentration gradients. We'll talk about that in this module. And then they can also recombine. And recombination results in an electron and hole annihilating one another. And we talked about that last time. We talked about carrier generation mechanisms and how carrier generation is measured and how it can be used to measure the bandgap of a material. And then we ended off with materials for light detectors. We talked about how the bandgap of a material is really important in determining what wavelengths it is sensitive to. So just to start off the class, I have a question for everyone. The question is, if you want to detect a certain wavelength, let's say I want to detect a 2 micron wavelength, okay? What would the corresponding, let's see, this chart will help you. If I want to detect, let's say, a 2 micron wavelength, which of these semiconductors is going to be able to detect a 2 micron wavelength? Exactly. You got it. You got it. Thank you, David. So to detect a 2 micron wavelength, we look at this portion of the chart and we can say that to detect 2 micron wavelength, that corresponds to a band gap of about, this is showing about 0.6 electron volts, 0.6 eV. The way that we got from the wavelength to the band gap is that we use this equation here, okay? We said that in order to detect a 2 micron wavelength, 2 micron wavelength, your lambda is equal to 2 microns. You convert that to an energy using the Planck's relationship. And so that is the energy that a 2 micron wavelength, light has. It's about 0.6 electron volts, roughly, using this equation. And then we say, well, in order for our semiconductor to be able to detect 0.6 electron volt energy light, the band gap must be smaller than 0.6 electron volts. All right, so that gives us only this material here. So it has to be smaller than 0.6 electron volts, because why? Because in our energy band model, the conduction band, and you have the valence band here, in order for an electron to go up into the conduction band, the energy of the incoming light has to be greater than the band gap energy. If it is greater than the band gap energy, then the light will be absorbed and the electron will go from the valence to the conduction band. So that process, that absorption process, doesn't happen if the energy of the light is less than the band gap. Okay? So I don't know if I told many of you where I was this week. I'm at a conference. I went to a conference yesterday. And I want to actually share with you one of the things I found at the conference, because it's actually very closely related to this slide here. I think at the end of class I mentioned that there's a lot of interest in not just detecting visible. Silicon can detect visible light pretty well, so most of our cameras are made of silicon. But there's also an interest in detecting IR. Does anyone remember why we'd want to detect IR? What type of applications might that be? Yeah, military and industrial applications. Yeah, exactly. Thank you. So it turns out at this conference, it was a military technologies conference that I went to. Can everyone see my Chrome window, browser window? Great. So there's this company called Service Optics Corporation that they're based in San Diego, and they've been doing work for the government and the military for the past 20 years. And what they can do is they have a technology. They use semiconductor cameras, specifically in the short wave IR and mid wave IR. So this is short wave IR would be, 1.5 to 5 micron wavelength. And then there's also the 1.5 to 3 and the 3.5 to 5 micron IR. So in order to detect this type of light, this is the material that they have to use, INSB, which is indium antimony. All right, and if we look up the band gap of indium antimonide, okay? It's a narrow gap semiconductor with an energy band gap of 0.17 electron volts at 300K and 0.23 electron volts at 80K. So if we look back to our little chart that we had, we can do that calculation also very easily. We see that 0.6 electron volts will allow us to detect IR radiation. In fact, INSB, this material that you see here, is exactly the material that the company is using. So what can you do with this kind of stuff? Well, you can do what's called infrared imaging. So for example, this is one application of a case study. They do spectral imaging for industrial flame monitoring. So let's say you have some kind of combustion process that's giving off heat as a result of the combustion. The EPA apparently has specific regulations regarding what you can do with flares in terms of temperature and in terms of materials that can be given off in the flare. And this is the type of information that you can get from it. You can actually have a movie running where you can see the different temperatures in the flare, and from that you can gain a lot of information about the combustion process and even what type of materials are being emitted. If you do spectral imaging in the IR range, you can actually get information about what materials are being emitted by the flame. That's just pretty neat. This is a video I saw yesterday, which is demonstrating how their technology works. I'm going to mute the video. But in this, if you look very closely here, you can see here that there's a plume that's coming off the smokestack there, and it's shown in red. Can't see it very well because of the way I took the video. But if you look here, look at this video, I'll just repeat it over and over again. The imager that they have, it detects the flare, and it shows it in a different color. And this is quantitatively telling you what the temperature of that region is. This is another example on the left here, where they're monitoring these flares. Okay, and they can monitor combustion that way. So this is all done with a semiconductor camera, not silicon, indium antimonide. It's obviously a lot more expensive than silicon because it's, the materials are more rare and the economies of scale just don't exist for that material. So they're more expensive, but it gives you a lot of cool capabilities. All right, so enough. Yeah, question? Oh, yeah, on the previous slide. Yeah. Oh yeah, that's a really good question actually. It's one I actually hadn't thought about, but let's work through it. If one of the things you'll notice about this graph is that it's actually exponential. So you see the numbers going up here. This is 1, 2, 3, 5, 7, and it actually goes to infinite by the time you get to 0. Because if you look at this equation here, E equals hc over lambda. A band gap of 0, an energy gap of 0 corresponds to hc over infinity, right? Hc is fixed, and the only way to get a 0 on the right side of the equation is to make your lambda go to infinity. So in principle, you should be able to detect any wavelength as long as you can find a semiconductor with a band gap smaller. If you want to detect 5 micron, you can use indium antimonide, but if there's a semiconductor with a really tiny band gap, then presumably you should be able to detect even higher wavelength radiation. But there's other effects that come into play also. If you have a super small band gap semiconductor, then at room temperature, if you guys remember what we talked about in the last module, even at room temperature, there's enough energy for an electron to go into the conduction band. So that's a temperature-driven transition. So this transition that we're showing here, that could be temperature-driven, or it could be light-driven. So when you go to really small bandgap materials, there's actually enough energy just in temperature to cause this effect to happen. So then your light sensitivity becomes really, really poor because it's dominated by the temperature. So those materials would have to be cooled down to really low temperatures in order to detect just the light and not the temperature. Okay, you'd have to get rid of this temperature-driven generation somehow, and you have to to get just the light-driven, you have to drive the temperature-driven generation all the way down. And that's why you bring those materials down to very low temperatures when you're trying to detect very high wavelength light. So I hope that answers your question, David. Yep, thank you. All right, so now let's talk about the next process. So we were talking about, we talked about carrier generation. Now let's go to talk about carrier recombination. All right, so the simple model for recombination is the exact opposite as generation. This is when you have an electron that's in the conduction band, and then you have a hole in the valence band, and that electron just comes back down like this, and then now after the recombination event, you no longer have the electron in the conduction band, and you no longer have the hole in the valence band, so they cancel each other out. Just like we talked about electron-hole pairs being generated in pairs, this is where they're being removed in pairs. So in the physical world, what this means is that you have the electron that's loosely bound to the lattice. So loosely bound means it can move around. A loosely bound electron is an electron that's in the conduction band. So when that electron happens to see a hole nearby, remember a hole is an incomplete bond. So an incomplete bond, it has one electron in it, but it's looking for another electron. So this electron happens to go by there. It sees that there's a low energy state, an energy state that it can hop into. It's happy there, so it goes in there, and when you do that, then that missing state disappears, and then you have a nice complete lattice. Okay, so this type of effect, this recombination, will happen on its own. It'll happen spontaneously because it's just an electron trying to go to its lowest energy state. All right, when we talked about Fermi-Dirac statistics, we said electrons like to be in the lowest energy state. Okay, so when this electron goes through this process, it goes from a high energy state to a low energy state like this, there's a certain amount of energy. That energy is equal to Eg. So the electron lost energy in an amount that's equal to Eg. And so that energy is given off either as light in the form of a photon. And when you give it off in form of a photon, then the energy of the photon is equal to hc over lambda. So you can determine the wavelength of the light that's given off. That's radiative recombination. The other type of recombination is just thermal recombination, where the recombination event generates heat in the material. The first process happens often with direct bandgap semiconductors, and the thermal process happens more with indirect bandgap semiconductors. All right. When we look at equilibrium, we'll talk about definition of equilibrium, steady state, and transient on the next slide, or in one of the subsequent slides here. At equilibrium is where the processes are balanced. So that means that generation rate is equal to the recombination rate. Okay. When the semiconductor is at equilibrium, this has to be true. So let's think about this for a second. You have a block of semiconductor material. Actually, let's draw the energy band diagram. So you have a bunch of carriers here. Electrons in the valence band. All right, and this at equilibrium, you have electrons that go up into the conduction band, and then they come back down. Another electron goes up into the conduction band. It might move around in the conduction band a little bit and comes back down. These processes are repeated over and over again. And so GI here is the generation rate. It's the number of generation events per second. Number of generation events per second. So the units for this would actually be 1 over seconds. All right, so that's the generation rate. The generation rate at equilibrium is equal to the recombination rate. So the recombination rate is the number of recombination events per second. All right, so now let me ask a question, and please, this time someone else answer, please, besides David. So David, thank you for all your, thank you for your participation, but I want other folks to also consider this. What would happen if the generation rate was greater than the recombination rate? Yeah, you just think about it for a second, that's okay. So imagine that there's generation events happening, so electrons are going up into the conduction band, but there's no recombination events happening. What would happen over time? Oh, sorry. All right, come on. Are you guys still there? Can you hear me? Make sure. All right, so how about someone just jot it down in the public chat? Or just blurt it out, either way. Would the flow of electricity stop? It could. Yeah, the flow, in principle, the flow of electricity could stop if this effect were to happen. Let's say, oh, we just lost that image. Okay, let's go to this image instead. That's fine. So let's say you have one recombination event and then you have more and more recombination events happening. If this kept on happening, you could see that eventually the valence band would be empty. And if the valence band were completely empty, then there would be no flow of electricity, as Trevor said. Right? So that process doesn't happen. Right? Now, I want you to think about why that doesn't happen. If you have, when you generate an electron, if you have a lot of generation events, if you have a lot of carrier generation events, you're going to generate a lot of carriers and a lot of empty states. Right? So every generation event creates an empty state, and it creates an extra electron. So if there's a lot of electrons and a lot of empty states, the probability that they come together gets much higher. Okay, so the more electrons, the more holes you have, the higher your recombination rate goes. So that's why the generation process and the recombination process eventually end up at equilibrium. So at equilibrium, the generation rate is equal to the recombination rate. These both have units of 1 per second. And it's equal to alpha r times n0 times p0. And just to remind everyone, n0 is the electron concentration. And P0 is the hole concentration. The more electrons you have, the more holes you have, the higher your generation and recombination rates are going to be. The proportionality constant is given by alpha r, and this is the recombination rate constant. So this rate constant is actually here. Alpha r is the recombination rate constant. That's temperature and excitation dependent. Higher temperatures, you're going to get more generation, more recombination. We went over that in the last module. Higher temperatures results in a higher generation rate. And if you have a higher generation rate, you're going to end up with a higher recombination rate because the two processes are in equilibrium with one another. So that process of electrons going up and coming back down, it just happens a lot more frequently at higher temperatures. All right, so we went over this question. In order to maintain equilibrium, the rate and rate of recombination and generation must be the same. If it were not the same, then eventually you deplete all the electrons in the valence band, and that just doesn't happen physically. Any questions about generation and recombination at equilibrium? You feel free to, if you have questions while I'm talking and you don't want to interrupt, like feel free to just add your question into this message window. All right, so moving on. All right, so this will be fun because we're doing this online. So I would like everyone to just give their best guess at these questions. We'll do it one at a time. The first question is, which of the following statements is false? The first statement is, when NP is less than Ni squared, the generation rate is greater than the recombination rate. When NP is greater than Ni squared, the recombination rate is greater than the generation rate. When NP equals Ni squared, the generation and recombination rates are the same. And the last statement is, equilibrium is when the generation and recombination rates are different. So I would like everyone to just type in their best guess, and then we'll go over it. Just for the first question, because the second question, we talked about this already. So second question is units for recombination generation rate is 1/seconds. All right, so let's see here. Okay. All right, universal D. Okay, great. That is correct. Thank you. All right, so at equilibrium, this N0 times P0 is equal to Ni squared. Okay, so these statements are actually all true. NP equals Ni squared is true at equilibrium. NP is less than Ni squared, that's when the generation rate is greater than the recombination rate. When NP is greater than Ni squared, the recombination rate is greater than the generation rate. So these are non-equilibrium situations in A and B. Statement C, this is at equilibrium, the generation and recombination rates are the same. And D, equilibrium is when the generation rates and recombination rates are different. That is false. This is false because at equilibrium, the generation and recombination rates are the same. Okay, so these two are non-equilibrium situations. Those statements are true. This is an equilibrium situation. That statement's also true. The units for recombination rate and generation rate are 1/second. So I might ask a question like, ask you to calculate what is the number of electrons being generated per second. We're going to have a question like that in this example here. All right, so generation and recombination events. So we're going to talk about what the process is that happens when you combine generation and recombination. And we've talked about this already, so this also makes sense, but we're going to do some more quantitative calculations of it. So the optical generation of carriers is typically followed by recombination. The generation event, an electron absorbs a photon of energy. Assuming that energy is greater than the band gap, the electron gains enough energy to move into the conduction band. Okay, once it's in the conduction band, notice that the arrow here goes way above the conduction band. That means the electron must have absorbed a lot of energy. So it's not just enough energy to get to the edge of the conduction band. This one's going much further than that. So the electron, that's part A. In part B, what happens is that the electron undergoes some scattering events. It loses some energy via scattering events and falls to the edge of the conduction band. Let's see what we mean by that. So the energy band model is shown here that the electron is going through this transition. It's going from higher to lower energy states. Okay, we've already said that electrons like to occupy the lowest energy states, but the one way we can think about this physically is that, remember that the electron is going through the lattice, and it might bump into or be deflected by a silicon atom. It could be, if the silicon atom has an orbital sticking off of it, then the electron could get deflected by the orbital, because the orbital has some negative charge associated with it. So those are scattering events. So scattering events are shown in the energy band diagram, and then this is the physical model there. Apologies for my terrible writing. So the electron loses energy via scattering events until it gets to the edge of the conduction band. So now the electron doesn't see any small or lower, so the next lowest energy state that it can go to is all the way down here. So the electron has to lose a lot of energy at the same time during this recombination event. All right, so as we mentioned before, this can result in a photon being emitted, can result in luminescence. So one quick question that I'd like to ask is, how could recombination experiments be used to measure the bandgap? So if you have a material of unknown bandgap, how could you do a simple light experiment to measure the bandgap? So let's have somebody else this time. All right, who's following along here? I can usually don't like the cold call, but there you go. Lama said speed and distance and time. Lama, could you expand on that? Oh, that was from before, was it? No, it's from that. So, Lama, are you able to, is your microphone working? Could you expand on that a little bit? Okay, Lama is typing something here. Okay, if we know the time and electron speed, we can calculate the distance. Okay, so if we know the time and the electron speed, there's actually an easier way to measure the bandgap, and that way is simply to measure the wavelength of the photon that's emitted. If this transitions is the energy Eg, then this is going to create the photon. The energy of the photon is going to also have an energy equal to Eg, and the photon will then have energy equal to Hc over lambda. And so we can measure lambda. We can measure lambda with a spectrophotometer or spectrometer, very similar to how the physicists did it back in the early 1900s when they discovered atomic spectra. Based on this wavelength here, we can measure the band gap of the material. Okay. Okay, good. So let's all look at this problem now. So this is an example of a 0.46 micron sample of gallium arsenide is illuminated with monochromatic light with energy equal to 2 electron volts. The absorption coefficient is alpha, is 5 times 10 to the fourth centimeters to the -1 power. So that's the units for the absorption coefficient. And the power incident on the sample is 10 milliwatts. And you're asked to find the total energy absorbed per second, the rate of excess thermal energy given up by electrons due to lattice collisions before recombination, and the number of photons per second given off from recombination events. So the first question here is about this portion of the process. Find the total energy absorbed by the material per second. The second question has to do with the scattering, the rate of thermal energy being given up by the electrons. So as the scattering event happens, how much heat is being generated in the material from these scattering events, lattice collisions. And then the third question here has to do with this process here, the number of photons per second given off from recombination events. So instead of asking you to measure the just the band gap, which would be an easy question, they're asking you to figure out the number of photons per second given off from recombination events. So this particular problem, there aren't that many calculations, but you do have to think a lot. So that's why it's good to go over this together as a class and help that explain the concepts. So let's just go through this one step at a time. Let's just focus on this part right now. Find the total energy absorbed per second. So we start off with the absorbance equation. Okay, I'm just going to draw on this window here because it'll be easier for you to see. So remember, we had the semiconductor sample. It had a thickness T. And so you had the incident light, I0, and then you had some sort of transmitted light, IT. And the transmitted light is what we can detect with the detector. All right? Now, there's some light that's absorbed here. We call that IA. So the conservation of energy states that the total energy, IO, is equal to IA, the absorbed energy, plus the transmitted energy, right? So you had a certain amount of energy going into the semiconductor. A fraction of it is absorbed and a fraction of it is transmitted. But the energy is not lost. It has to just be converted to other forms. So some of it's absorbed and some of it's transmitted. So this conservation of energy has to hold true. That's the first portion of it. So it's now asking you to find the total energy absorbed per second, joules per second. So we will use this equation, I0 is equal to IA plus IT, rearrange that into this form. IA is equal to I0 minus IT. Okay, also remember that this, from earlier in this module, what we call the absorbance law, IT is equal to I0 e to the negative alpha t. So I've drawn t in this equation. In this answer, they use L. So just replace the t with the L here. So IT is equal to I0 minus IA. So we're trying to solve for IA. So IA is equal to I0 minus IT. And then IT is equal to this. So we put those together and we get I0 minus I0 e to the negative alpha t. And then the IOs can come out here, I0, 1 minus e to the negative alpha t. Okay? So we have an equation to find IA. So it's equal to I0 times this exponential term. IO minus, same equation here. IO is equal to 10 milliwatts. So just let's remind ourselves of units here. 1 milliwatt is equal to 10 to the negative 3 watts. A watt is equal to a joule per second. 1 joule per second is equal to 1 watt. It's a measure of optical intensity. Not optical energy, optical intensity. Optical energy is the E, right? So light has E equals hc over lambda. So small wavelength light will have high energy. So the energy has to do with the energy that each photon has. The intensity of the light has to do with how many photons per second is coming in. So we can convert watts into the number of photons per second. We'll get to that in a second. All right, so let's get back to this problem. So 10 milliwatts is our I0. The thickness of the semiconductor material is given to us as 0.46 microns, so 0.46 times 10 to the negative 4 centimeters. 1 micron is 10 to the negative 4 centimeters. Okay, and the alpha, we were given that as well in the problem, 5 times 10 to the negative 4 to the centimeter negative 1. So notice that these units, centimeters and centimeter to the negative 1, they are inverse of each other, so they cancel when you multiply them together. Okay, and then you take the exponential of that and you're left with 1 minus 0.1. So this gives you 9 milliwatts, 10 times 1 minus 0.1 is 9 milliwatts. Okay, 9 milliwatts is 9 times 10 to the negative 3 joules per second. So that is the amount of energy being absorbed during this phase of the process. The second phase of the process is the scattering due to the generation of thermal energy due to scattering events. So this scattering up here, it generates heat. This scattering down, this recombination event generates light. Okay, because this is a big energy transition. Big energy transitions have enough energy to release a photon in radiative materials, direct bandgap semiconductor materials. And these small energy transitions, this is just a bunch of small energy transitions instead of one large one. So those small energy transitions is not enough energy to generate a photon. All right, so find the rate of excess thermal energy given off by the electrons due to lattice scattering, lattice collisions. So the second part here, we find the rate of thermal energy. And this is actually a quick problem to do. The way you do it is you consider that the percentage of energy converted to light is a fraction of the energy that was absorbed. Let me explain what I mean. So in the problem, sorry, I'm switching back and forth here. It absorbed light with energy 2 electron volts. So this distance here is 2 electron volts. That's the energy that the electron gained. Now some of that energy, the energy shown by the squiggly line here going downwards, that energy is lost to thermal scattering events, and the remainder is lost to the light emission. So this is 1.43 electron volts. So the remainder of this here, 2 electron volts minus 1.4 electron volts is 0.6 electron volts, roughly. So what this energy band diagram tells us is that every electron generates, every electron that's absorbed and generated up here, it will generate 0.6 electron volts of heat and 1.43 electron volts of light energy. So the ratio of the two, 0.6 divided by the total, is the percentage of energy that's converted to heat. This quantity, 1.43 divided by the total, is the percentage of energy that's converted to light. All right, so let's go to this again. The percentage of energy that's converted to light is 1.43 electron volts divided by 2 electron volts, that's 0.71, 71%. And the percent that's converted to heat is 2 electron volts minus 1.4 electron volts. This is the 1.6 electron volts that I was showing you in the last slide. Divided by 2 electron volts is 28%. So it's almost a 70-30 mix there of light conversion versus heat conversion. So we're only concerned with the heat in this particular part of the problem. So the thermal energy per second is 9 milliwatts times 0.28 times 0.28, not 0.28%. That would be much lower. 9 milliwatts times 0.28. That's 2.5 milliwatts, or 2.5 times 10 to the negative 3 joules per second. So that's the amount of energy being given off. Now, the last part asks about the number of photons per second given off from recombination events. Now, keep in mind that the question didn't ask you the more basic one. The basic question would be, just like part B, what's the rate of optical energy generated? The rate of optical energy generation is just what we found on the previous part of the problem, right? 71%. Right? You figure out the ratio of what the band gap is divided by the energy absorbed by the electron, according to that model that we just drew. And so that's 71%, or 6.4 times 10 to the negative 3 joules per second. All right. But this problem is asking you to go one step further. It's asking you to convert the power into photons per second. Notice it's asking about the number of photons per second that's being given off. Okay, now to do this, we know that each photon has 1.43 electron volts of energy, right? Because in your band diagram, there's a 1.43 electron volt band gap. So when that photon transitions, when it does that second step, it loses 0.6 electron volts up here, and then the transition here, it loses 1.43 electron volts. So every photon that's being generated has 1.43 electron volts of energy. We know the rate of energy that's being given off, and we can just combine the two to figure out the photons per second. And what we're doing here is a unit conversion. It's a simple unit conversion problem. The number of the photon recombination rate, or the photon emission rate, which is equal to the recombination rate, 6.4 times 10 to the negative 3 joules divided by 1 second, multiplied by 1 electron volt over 1.6 times 10 to the negative 19 joules. So what are we trying to do here? We are just trying to convert from joules per second. So we are given, if we look up here, we know that the power being converted to light is given in joules per second, and all we're trying to do is convert that into photons per second. So 6.4 times 10 to the negative 3 joules per second, we're multiplying it by some conversion factors. The first conversion factor is the units of energy. 1.6 times 10 to the negative 19 joules is equal to 1 electron volt. That allows us to get rid of the joules and convert that into electron volts. And the next unit conversion is that we convert electron volts into photons, because every photon gives off 1.43 electron volts of energy. So by multiplying it by this factor here, we can get rid of the electron volts, and now we're left with photons per second. Okay, so we divided by 1.6 times 10 to the negative 19, divided by the band gap, and we're left with 2.8 times 10 to the 22nd photons per second. Okay, so math is relatively straightforward here. It's just all conceptual. This question is all conceptual. All right. Let me check to see if there's any questions. Sri, no, I could not hear you. Let's see, are you still on here? Okay, yeah, I could not hear you, but it might be an issue with the microphone, but feel free to just type in your questions or responses if you'd like. So I'll continue there. Were there any questions on how to solve this problem? If so, just add something here and I'll move on in the meantime. I'll come back and check on that. All right. So we are at 6:30 now, so let's continue. All right. There's two types of recombination, as I mentioned earlier. One happens in direct bandgap semiconductors, such as gallium arsenide. The other one happens in indirect semiconductors. And I just want to open up the last PowerPoint so you can mind yourselves. This one. So in this slide from the last module, we said that one of the things that distinguishes indirect from direct bandgap semiconductors is that the minimum of the conduction band, which is where most of the electrons are at, aligns with the top of the valence band where most of the holes are. So in a direct bandgap semiconductor, the electron just has to transition in energy. In an indirect bandgap semiconductor, it has to transition in energy, and then also has to transition in momentum. So it has to move in the vertical direction and the horizontal direction. This is momentum on the x-axis. So because it has to change, it can't change both simultaneously. The processes happen one at a time. So the way that it's represented in a basic energy band diagram. Oops. Where is it? There you go. The way that it's represented in an energy band diagram is like this. We'll go over each one in turn. The direct band gap is what you saw earlier. So you get the absorptions, maybe some loss due to scattering events, but the recombination event happens here, and it's just shown as a direct transition here. So this occurs in direct band gap semiconductors like gallium arsenide. The energy loss from recombination is often converted into a photon, and it's typically fast because there's only one energy transition. Indirect recombination is through an intermediate energy state. So the electron can't transition momentum and energy at the same time, so it does it in a two-step process. In a basic energy band diagram, this is how it's represented. The electron goes from the conduction band down into an impurity state, a dopant level state. I'll go over this in a second. So this first transition happens if you assume that there's some sort of a trap level within the band gap due to impurities. Remember that silicon doesn't create any energy states in the band gap, but if there are defects in the crystal or dopants, those can create some of these extra states in the band gap. So the first step that happens, the electron, instead of transitioning all the way down to the valence band, it transitions to the trap level. right? So, and then a different electron could transition from the trap level into the valence band. So it's happening in a two-step process. There's two steps, so it ends up being slower. This electron might recombine here, but then it might take some time for the second recombination event to happen. So that indirect recombination involves two steps, so it's slower. The energy loss is often converted to heat, and it typically occurs in indirect bandgap semiconductors. All right. These are typical impurity and trap levels. There was something like this on the previous module as well, but I thought this would be helpful for you to see again. Lithium, phosphorus, arsenic, antimony. These are all materials that are common N-type dopants. The ones that are very close to the valence band, boron, gallium, and aluminum, those are common P-type dopants. And there can also be a lot of energy states in the middle, too. For example, if you have gold, if you have some gold contamination in your process, or if you have some zinc contamination in your process, this can create ions. So let me tell you what I mean by impurities, or unintentional impurities. So you guys have seen pictures of silicon wafers, and the silicon wafers that have the computer chips on them. They are made using a process that puts, it'll create an N-type material here, and then it'll create the source and the drain here next to it. So a lot of these processes are done at the surface of the semiconductor, and it involves actually dipping the semiconductor into a variety of wet or dry etching, dipping the semiconductor into water multiple times to clean it during the process. The typical process is like 100-some steps of processes such as etching, electrochemical deposition, vapor deposition of semiconductors and metals, electrodeposition of metals, and so forth. So after those processes and after photolithography processes, there are often rinse steps where you're cleaning it off. It's cleaned with water. If your water happens to be impure, if you haven't cleaned the water well, you can get atoms. You can get like gold atoms, let's say, gold ions, just at the surface. So those types of impurities could actually wreak havoc on your system because it could create a trap state within your bandgap, and that will cause indirect recombination events happening more frequently than if you did not have a trap state in there. So sometimes you intentionally want to have a trap state so that you can encourage a certain type of recombination over the other. But they can also be unintentional too. I just gave you an example of a case where you don't want the trap state, but because you didn't have clean water, you messed your semiconductor up. And this gold contamination, I remember one of my teacher's advisors telling me that this gold contamination was a big issue in microprocessor development, and they were not able to make reliable microprocessors until they solved that problem. So it is an issue of practical concern. Okay. So let's talk about photoluminescence now. Photoluminescence is when you use light to, let's just compare the three types of luminescence. Photoluminescence is when light is used to excite the carriers and the light is given off by the semiconductor. Electroluminescence is when the semiconductor is excited with an electric field, and then it gives off light. So electric current used to generate light. That's an example of LEDs. Cathode luminescence, which is not covered in this class, is that the carriers are generated by bombardment with high energy electrons. And this is one of the things that was used to, in old style displays, some of the big heavy TVs that you may have seen from the 1980s and 90s, those were made using cathode luminescence technology. And those TVs obviously are not used anymore. Photoluminescence, I don't think I didn't go into the details of that. That's where light is being used to excite the carriers, and it's also giving off light. Examples of that was a fluorescent lamp, where you're exciting the phosphor material with ultraviolet light, but then what's actually coming out of the tube is visible light. Okay, other examples of that is just other phosphor materials that glow in the dark. That's an example of like photoluminescence. So the reason we're bringing this up again is because we talked about recombination events. Luminescence events happens during this recombination process. Here's some examples of luminescent materials. The LED is one of the big successes of solid-state devices. There are LEDs available that can emit light in almost any region of the visible spectrum, and now they have LEDs that can do ultraviolet and infrared as well. So it's been a big breakthrough in the sense that these can be light-generating materials for various types of scientific experiments, thermal imaging, and so on and so forth. So this is just a chart of, these are examples of some LEDs. This is a review article from 2008, which talks about all the different wavelengths of LEDs that are commercially available. And this chart here from this diagram from Wikipedia, it shows how a light-emitting LED works. We're going to talk about the band structure for a diode. What's unique about about a diode is that there's some recombination events that happen within at the middle in between the P and the N regions, and those recombination events generate light in a semiconductor, a direct bandgap semiconductor. Another example are quantum dots. These are small photoluminescent materials made from a specific semiconductor called cadmium selenide. We're not going to get into the details of this, but CDS is a material where if you make it really small, if you make the particles, close to, well in the submicron range, then the emission of the wavelength is determined by the particle size and not by the band gap. This is because of quantum confinement effects. Like I said, this is beyond the scope of this class. But the quantum dots are widely used in biological research and fluorescent tagging. You can see here that they get super bright. This is one of the reasons why they were of great interest to biology, people doing biology, because they were so bright, it made things very easy to see. But the issue was there's a toxicity issue with quantum dots, and that's one of the reasons they're not used so frequently anymore. There's, just regular fluorophores are used instead. We're not going to get into what fluorophores are. That's beyond the scope of this class. But quantum dots did find another application, and that was in televisions. Some of you have heard about the Q dot display. If not, I'll just do a quick Google search on it. Quantum dot display. I think Samsung. Yeah, Samsung has it. There you go. Yeah, if you look up quantum dot displays, you can see this is the quantum dot image that's from the slides, and they can make TVs out of them now. And one of the reasons why they're of interest and why they're so expensive right now is because they give extremely bright and saturated colors. And because of that, they can make a very nice quality TV. It's just that they're fairly expensive at this time. I saw some questions, so let me take a look at that. David, is cathode luminescence also a solid state process? Good question. So I would say yes, because you're bombarding the solid state material with electrons. Those electrons are coming externally. Okay, so, but the process of light generation is happening in the semiconductor material through the same processes that I went over. So I would consider that a solid state process. Yes. Thanks for that question. Great. All right. So let's now get into the different types of stimulus in electronics. Some of this may be familiar to you from if you remember your Circuits 2 class, where you're taught about like AC and AC analysis, harmonic analysis, transient analysis, and so forth. It applies to semiconductors because in this module, we are going to be talking primarily about optical stimuli. We're going to be shining light in a semiconductor material, and we want to see how that semiconductor material responds to the light. So there's various types of light stimuli that we can apply. So there's, one type of, the simplest example is where we apply no stimuli at all, and just an equilibrium semiconductor. That's what we did in the previous module. We calculated electron and hole concentrations in the equilibrium material. So in this module, again, we are interested in N and P. We're interested in the electron and hole concentration under these various conditions. So at equilibrium state, we call those the N0, P0, the electron and hole concentration at equilibrium. And then we're also going to be looking at the electron and hole concentrations with constant stimulus and with time-varying stimulus. So example of constant stimulus would just be like a light. You shine a light on the semiconductor, is generating electron and hole pairs. And the intensity of the light doesn't change with time. It does not change with time. So that's an example of steady state stimulus. And then in the third case, the most general case is where you have a time-varying stimuli. All right, so you have a stimuli and it happens to be time-varying. That's the transient case. All right, so this is where your, here, let me just put down some notations here that we'll go over again later, but I'll just put it here anyway. So we're going to have something called sigma n, sigma p. Sigma n and sigma p are excess electrons and excess holes that are generated by stimulus. In the case of a constant stimulus, the sigma n and sigma p are constant because it's a constant stimulus generating constant excess of electrons and holes. In the transient case, we also have sigma n, but now it's a function of t. It's a function of time. So the carrier concentrations are going to vary with time. So that sigma stands for the excess electrons, excess holes. We'll go over more of that later. But just so you know here that there's these three types of stimulus. The rules of these three different types of stimulus, at equilibrium, there's no external excitation. We're at constant temperature. So as a result, at equilibrium, there's no net current. Carrier concentrations don't change with time. The steady state case, you're applying an external stimulus, but it's constant in time. So you can have carrier generation, but they're balanced by recombination. So each process has an equal and opposite process at steady state. And the most general is the transient case, is when stimulation changes with time, and in this case, the carrier concentrations and currents can change with time. So all these are summarized in this slide here. Oops. So in equilibrium, you look at the type of stimulus, the carrier concentrations, and the currents. This summarizes the statements I made up here. We're looking at light stimuli. There can also be electric field and temperature stimuli being applied. But these general concepts, time varying, constant, and no stimuli, apply in all fields of engineering, really. All right. So now let's talk about the carrier lifetime. This is the carrier concentration in response to a pulse of light. So if you have a time varying stimulus, transient case, let's see what happens. So I want you to think about this in terms of the physical process. The first thing that happens is when you shine light in the material. The first thing that happens is that you're going to illuminate the semiconductor material with light. So you imagine, there we go. So you illuminate the material with light. And when you illuminate the material, you're going to generate electron-hole pairs everywhere. Okay, so at that first stage, you're generating all these excess carriers. All right, remember, I'm not drawing, even before you shine light on the semiconductor material, remember that there is, of course, electrons and holes. Right? There is already electrons and holes there, but these are considered the base levels, or the equilibrium levels, equilibrium levels of electrons and holes. But let's ignore those for now. Let's look at the excess electron and hole concentration. When you shine light on the material, you're generating additional electrons and holes due to the generation process. And so that's what's shown here. When you generate the light, this is an important equation to remember. We're not doing the derivation of this, just remember it, is that the excess electron concentration is equal to tau n times GOP. What are these? This is the carrier lifetime. It's the carrier lifetime, and this is the carrier generation rate. So the units for carrier lifetime is seconds. And the carrier generation rate is 1/1, sorry. Carrier generation rate is 1/seconds times centimeter cubed. Because it's electrons per centimeter cubed per second. That is the units for the carrier generation rate. When you multiply these two together, they cancel, and you're left with 1/centimeter cubed. Okay? We'll talk about steady state generation on the following slide, but let's look at the carrier lifetime question. You shine the light on the material, you generate these excess carriers. They can be calculated by this equation here, a sigma n0 and sigma p0. Now, you turn off the light. When you turn off the light, then these electrons and holes, these excess electrons and holes that you've generated, they will tend to recombine over time until you reach the equilibrium concentrations, which is the concentrations before shining light on the material. So, I'm sort of illustrating this here. If you look at this spot here, there's a recombination event, another recombination event, another recombination event, and they eventually all disappear until you're left with the base material again. So the rate at which the carrier concentration decreases, the excess carrier concentration decreases, it turns out that it's an exponential decay versus time. So initially, your excess carrier concentration, your excess electron concentration was sigma n0. And then when you turn the light off, it immediately starts to decay to 0. Okay, and when your excess carrier concentration is 0, then you're left with just your base or equilibrium levels. So this, the rate of decay, any type of exponential curve like this has a rate constant associated with it. So the equation for this curve looks like sigma n0. That's the initial value up here, sigma n0, e to the negative t over tau. So this tau determines, that's the carrier lifetime. It determines the rate of decay of this line. So this would be a very fast rate of decay. This would be a slow rate of decay. So this would be where you have a very fast recombination rate. And the second one here would be where you have a very slow recombination rate. And so slow recombination rate means increasing tau. If you have a long carrier lifetime, you have a faster recombination rate. So the way that carrier lifetime is defined is that carrier lifetime is the average time between generation and recombination events. Okay, I mentioned that at the beginning of the module. I'll mention it again here. Carrier lifetime is the average time between generation and recombination events. Here's a quick way we can generate a relationship for the carrier lifetime. So we have that problem that we showed, the example that we showed in the previous slide. You generate a flash of light at time equals 0, and then you turn it off. What's the resulting carrier concentration as a function of time? So we basically are trying to find the equation for this here. You start off with the rate of change of excess carriers. So you use a statement of charge conservation. So the rate of change in the excess carrier concentration is equal to the generation rate minus the recombination rate. This is a typical differential equation that shows a rate. It's, the way you can think about it is GI is generating carriers, RI is removing carriers. So the difference between the two is how gives you the rate at which carrier concentration would change with time. I'll have another example of this when we talk about the continuity equation later. All right, so d sigma n dt, you plug in the generation rate and you plug in an equation for the recombination rate. Notice that the recombination rate is n0 plus sigma n, p0 plus sigma n of, sorry, I have a typo here. Okay, this should be sigma p. So the generation rate was given before by the equilibrium equations. The recombination rate is a little bit different. Notice it's not just N0 and P0 here. Let's go back up to the slide where we talked about generation and recombination rates. Here we said the generation rate, recombination rate is equal to alpha R times N0 times P0. The more electrons you have, the more holes you have, the higher your generation and recombination rates are going to be. In equilibrium situations, G, I, and Ri are the same. In non-equilibrium situations, Gi and Ri may be different. At steady state, they're also the same. All right. So the recombination rate is equal to N0 plus sigma n times T. It's increased because of the excess electrons and holes that you have. Okay, so when you solve this differential equation, you don't need to know the derivation for the purposes of this class. Don't worry about that. But I just want to put in what the assumptions are. If you solve it under the conditions where P0 is much greater than N0, or N0 is much greater than P0, so in essence, if you assume that you have a doped semiconductor, so one of these is much greater than the other. And the second assumption you make is low-level injection, which is, the excess carrier concentration, sigma n, is much less than the majority. So you're not changing the electron or hole concentration by a significant amount. You're only changing it by less than 10% or so. If you solve the differential equation under those conditions, you get these two equations. Sigma n of t is equal to delta n e to the negative t over tau. And that is the equation that we saw here. So this sigma n0 is also called delta n and e to the negative t over tau. So that just decays over time. Okay. And then the actual value for tau n is 1 over alpha r times n0 plus p0. Okay, you don't need to know how this was derived. You just need to know how to use these equations. Right? You have to know what carrier lifetime is. Here's another example. So we have we're talking here about majority and minority carrier concentration due to an instantaneous pulse. I'm going to draw it simply here. So we have a p-type gallium arsenide doped with 10 to the 15th acceptors. The concentration of electrons is 10 to the negative 3, right? This is calculations that we've done earlier. Like if I give you the doping of a semiconductor material, then if I tell you that you should be able to figure out the electron and hole concentration. So here I told you that you have a semiconductor material that is doped to 10 to the 6th, and you can easily calculate the electron and hole concentration based on the NP equals Ni squared formulas I shared with you earlier. So that's at equilibrium. Now we apply a pulse of light that creates 10 to the 14th electron hole pairs per centimeter cubed at time equals 0. So what is the electron and hole concentrations versus time? So let me just go through real quickly how to do that problem. You'll have another problem like this in your homework, so let's just go over this one quickly as a class. I don't have all the calculations here, so let's see if we can just do that real quick. So 10 to the 14th electron holes per centimeter cubed at time equals 0. So let's put in our electron concentration. Our hole concentration P0 equals 10 to the 15th per centimeter cubed. Remember, P0 is your equilibrium carrier concentration. So this is without light applied, before light. Okay, so P0 is equal to 10 to the 15th over centimeter cubed, and our electron concentration, we just figured that out, is equal to 10 to the negative 3 per centimeter cubed. A pulse generates 10 to the 14th electron hole pairs at time equals 0. So the process that you would do here is you figure out your delta n is equal to tau n times the rate generation constant. So the carrier lifetime. I think we need a piece of information here. this problem we actually end up doing later in the problem. Oh, I'm sorry. That's where I got confused. We're actually doing a very similar problem in the homework later. So let me just go over this example quickly, qualitatively, no calculations, and then we'll do the one with calculations a little bit later. What time is it? Okay, 10 minutes. So the first thing you notice is that the hole concentration increases here. The electron concentration also increases. So if you shine light on the material, you're going to generate excess electrons and excess holes. So the hole and electron generations are going to be the same in magnitude. But an important but subtle point is that compared to the equilibrium concentrations, it's a question of what is the fractional change of the electron or hole concentrations. You can see here that you had a p-type gallium arsenide, so the equilibrium concentration of holes, N0, or I'm sorry, is doped with p-type with 10 to the 15th, so the hole concentration is 10 to the 15th here. And by shining light on the material, you increased it by just a slight amount here, shown on a log scale. 1.1 times 10 to the 15th, that's the amount of electron-hole pairs that you have total. Okay, where's that coming from? You have 10 to the 15th coming from the equilibrium concentration, and then you have an additional 10 to the 14th electron-hole pairs per centimeter cubed due to the light being shined on the material. That's why you see this go up at time equals 0. When you turn off the light, the carrier concentration decays down to the equilibrium value over time. So t equals 0 is where you shine that light pulse on there. The next line here shows the electron concentration, and notice this is on a log scale. So what happens with the electron concentration is that initially you have 10 to the 14th electrons at t equals 0. The reason is because the electron concentration is very low. It's 10 to the negative 3. The equilibrium concentration is 10 to the negative 3. If you then add 10 to the 14th electron-hole pairs, electrons per centimeter cubed due to the light, that's going to, the majority of your electrons here are going to be created due to the light. Okay, so here, if you looked at the hole concentration, you can see, like on a log scale, it just changed. The fractional change was perhaps like 10% or so. It was a 10% change before the light. Before the light, it was 10 to the 15th. After the light, it was 1.1 times 10 to the 15th. So it's just a 10% increase in the majority carrier concentration. The hole is the majority carrier. And the minority carrier, the electrons, it's minority because there are fewer electrons in the system. It has a p-type doping, so there's fewer electrons. The minority carrier concentration, the fractional change is very significant. Okay. Let me check if we have any quick questions here. Okay, no. So the message here is that the fractional change in the majority carrier concentration is small. The fractional change in the minority carrier concentration is large. I went over this earlier. Sigma n0 is equal to tau n times GOP. So this is the excess carrier concentration when you turn the light on. It quickly reaches this steady state value. Okay, I already talked about the equation for that. It depends on the time constant and the carrier generation rate. So the higher time constants means less recombination. GOP is the generation rate. So if you have a high generation rate and less recombination, so a large time constant, then you're going to have a large excess carrier concentration. Okay. Okay, in the last 10 minutes or so here, we can just cover this. the steady state generation and recombination. This is an example problem, so we'll go through all the math of it. So we're shining laser light on an N-type material. So at T is less than 0, we just have silicon material. Okay, some of this is going to be a repeat of that last problem. T equals 0. Oh, okay. Yeah, so at T is less than 0, we're shining light on the material. All right, and we shine the light on the material, we create electron-hole pairs. So we have, we create excess carriers, sigma n and then sigma p. At T equals 0, we'll get to that in a second. Let's do the first part of this problem first. We're shining laser light on a material with an N-type silicon wafer so that the irradiated areas 10 to the 13th electron hole pairs per centimeter cubed are created every microsecond. Assume that the silicon has a doping of 10 to the 14th per centimeter cubed. Okay, so forget this T equals 0 just for the time being. We'll get to that in a second. So before irradiation, without the light, let's do the without the light here. Oops. So without the light, you're going to have N0 and P0, so no light. And then here is with light. So you're going to generate an excess electron and hole concentration when you add the light in the system, and the total concentration is going to be N is equal to N0 plus sigma n. And then the hole concentration is going to be equal to P0 plus sigma p. All right, these are the equilibrium values that were there before the light, and they also exist after the light. When you add the light to it, you're generating excess electrons and excess holes, so the total N is equal to the initial amount, the equilibrium amount, plus the excess amount. And the same goes for the holes. So you're asked to calculate the excess hole concentration created by irradiation, and then the total concentration after irradiation, and the percentage change. So we'll just go through this calculation real quick. 10 to the 13th electron hole pairs, this is the generation rate. So this is your GOP, the optical generation rate. You're given your tau n and tau p, and then you're also given the doping. So before irradiation and after irradiation. I don't know if you guys have this written down in your notes or not, so please, please do write this down. I just wanted to leave it blank so you can fill it in yourself. So before irradiation, you figure out N0 and P0. This problem you already know how to do from the last module. So you doped at 10 to the 14th per centimeter cubed, that's your doping density. And so your electron concentration is also 10 to the 14th per centimeter cubed. To figure out your hole concentration, you use NP equals Ni squared. Solve that for P0. Get 1.5 times 10 to the 10 squared divided by N0, 10 to the 14th, and you're left with 2.25 times 10 to the negative 6 per centimeter cubed. So this is your electron and hole concentration before turning the light on. And then after turning the light on, your excess carriers are going to be equal to sigma n is equal to tau n times GOP. Your tau n, okay, let me show you what's happening here. This is just a little bit of a unit conversion we have to do here. They're giving you the tau n and tau p in microseconds. Okay, so if we do our unit conversion, sigma n tau n times GOP. The GOP is given to us in EHP per centimeter cubed per second. And this is given to us in microseconds. So we just have to convert this microseconds to seconds. And the way we do that is just by dividing by 10 to the negative 6. So at 10 to the 13th microseconds is a carrier lifetime, divided by 10 to the negative 6. And so you get and you multiply this by 2 times 10 to the negative 6. This is the optical carrier generation rate. And then this is your excess electron concentration. The excess hole concentration is equal to the excess electron concentration, and that's also 2 times 10 to the 13th, because they're being created in pairs. All right, so your sigma n is equal to sigma p, and the total carrier concentration is n is equal to n0 plus sigma n, and you get 10 to the 14th plus 2 times 10 to the 13th, and so the total is 1.2 times 10 to the 14th. So in this case, this is an n-type semiconductor. This is the majority carrier. This is the minority carrier. Whichever one you have more of, that's your majority carrier. So the electrons, the majority carrier, and we've created some excess, and you can see that the electrons increased by about 20%. You started off with 10 to the 14th here, you can see here on the left, and after adding the light, it went up to 1.2 times 10 to the 14th. So the number of electrons increased by 20%. The holes, so the holes started off at 2.25 times 10 to the 6th. It started off at a pretty low concentration. Now you add your sigma p, you get, if you add 2 plus 10 to the 13th, add 2 times 10 to the 6th, that's obviously like many, many orders of magnitude smaller. So P0 plus sigma p is approximately equal to just sigma p, which is equal to 2 times 10 to the 13th. So if we compare before and after, fractional change, percentage change, before we had 10 to the 6th, now we have 10 to the 13th. So there was a seven-fold increase. I'm sorry, not sevenfold, 7 orders of magnitude increase in the numbers of holes, hole concentration, when you shine light on the material. Whereas the fractional change in electrons changed only by 20%. So this is what's called, minority carrier injection. You're significantly impacting the minority carriers, but you're not significantly impacting the majority carriers. Okay. All right. So I guess this will stop here for today. Yeah, we'll continue next class with quasi-Fermi levels. All right, let's give that a second. I just want to point out a couple things here. On Canvas, if you look under modules, I've posted the notes, and I've also posted homework 4, so you can get a start on that. You can take a look at the first part of homework 4. I will be posting the answers to homework 3 shortly, probably today or tomorrow, so that you can start taking a look at those solutions, and I will post the solutions to homework 4 probably this weekend, so you can start taking a look at those in preparation for the exam. The exam, again, will be on the 21st, Monday the 21st of October, so be prepared for that. If there's any questions you have on the homeworks or on the lectures, please do feel free to email me or whatever, and we can go over it in class next time also. The conference recording will be available here. Just like we have a recording that was posted earlier, you can watch the recording through here. The lecture is also going to be posted once I end the conference. I haven't done that yet. And it'll also be posted to YouTube like before. So you can always go to the YouTube site and see our lectures. Okay, any questions before we conclude the class? Okay. All right, I'll take that as a no. All right, well, have a good weekend, and I will see you all on Monday. Thank you. Have a good day.